So yeah, if you think back 2 months ago, we had this introductory talks by postdoctoral members, and I mentioned back then a particular result. So now you can stop holding your breath. I'm going to tell you how something like this is proved. So we have new monotone circuit lower bounds, this time for a really easy function, XOR SAT. So it's a function that, well, you can solve using Gaussian elimination. And this kind of a result says that monotone circuits can't do Gaussian elimination. You require exponential sized monotone circuits.
So what is that? Parameter or?
So, okay, I was debating what to put here. It's really a positive constant here. I haven't worked out what it is. In fact, you would conjecture that the true bound is really just exponential in order n. But our proof technique is a bit sloppy, and you lose some polynomial factors in the exponent.
Is it an interesting open question?
Yeah, it's one of my favorite ones, actually. Well, if you think back to last week, I had open problems there. One of the major ones was to prove lifting theorems for constant size gadgets. And if you had an appropriate constant size gadget lifting, you would get optimal bounds here. Maybe I'm jumping in the gun a little bit. But yeah, something like this, it's proved again by a lifting theorem. Last week it was all about how communication protocols and decision trees can be related by lifting theorems. This is also such a lifting theorem, but now for a pair of models that don't really seem like a communication query pair. So we're going to prove lower bounds for monotone circuits, starting from lower bounds in this well-known propositional proof system called resolution. I'll maybe explain or define it carefully later. But what's so amazing about this is that so far the two models, they're both DAG-like models. And the amazing conceptual connection here is that you can capture both models in the language of, well, communication complexity and query complexity. So I'll start with really explaining why this is the case. So there will be a query to communication lifting theorem between these models. And at least to me, since I didn't really know of these alternative characterizations for these models roughly a year ago, it came to me as a surprise that you can actually view them in this framework. And then it's kind of intuitively obvious that there could be a lifting theorem. So I want to start by rephrasing, giving a characterization of monotone circuits in the language of communication complexity. The characterization will be using some kind of an extension of communication protocols to DAG-like communication models. So, okay, there are many names for these guys. I maybe call them rectangle DAGs, but you can also call them DAG-like communication protocols. So, okay, last week we talked a lot about computing Boolean functions. In this context, we are always trying to solve a search problem. So it's a slightly different kind of a setting. So I already define such a model as solving a search problem. So abstractly, a search problem is just a relation where I have some set of inputs to Alice, some set of inputs to Bob, and okay, rather than finding a Boolean output now, there's some set of solutions. And they just need to find on any inputs x and y some output symbol that is in this relation. This really abstract setting for now. I'm going to specialize the search problem to something that is interesting for monotone circuits. Actually, let me define a concrete search problem, which you can define for any Boolean function or monotone Boolean function, depending on whether you study monotone or non-monotone complexity. But let me just do it in the monotone case, because that's where we can prove lower bounds. So these are called KW games, or KW search problems. Kachma and Victorson, yes. So the plus means monotone. There's, again, a non-monotone version. So the input here, you define it relative to a monotone Boolean function. So f here is just, let's say, it maps n bits to a single bits. Okay, and it's monotone in that if I look at two inputs that are bitwise ordered like this, every bit of x is at least the corresponding bit of y. The output is also ordered similarly. So in this search problem, the input is a yes-no pair of inputs. So x is a yes input, y is a no input. So Alice holds a yes input, Bob holds a no input. They're two different strings, so of course they must differ somewhere. And even stronger, because these two strings come from a monotone function, it actually holds that they must differ positively. So there must exist a coordinate where, okay, I guess this should be swapped, but a coordinate where the yes input has a 1 and the no input has a 0. So the search problem is just to find such a coordinate. So find a coordinate such that the yes input in that coordinate is a 1 and y is a 0. I should mention, if you define it for this for general functions, not the monotone version, you would just be looking for a difference. But this is a harder search problem. You're looking for a monotone difference. So when we're trying to characterize monotone circuits using these rectangle DAGs, these DAG-like protocols, this is the search problem you would be looking at. So I want to derive this upcoming model by kind of extracting the definition out of a circuit. So I want to somehow abstract what does it mean for a monotone circuit to solve this kind of a search problem. Okay, so it's a DAG, this model, and each node of the DAG comes with a feasible set of inputs, which is a rectangle. So each node in the DAG has what I term a feasible rectangle or a set. Okay, so this is some product set, some set A times B from this input domain. And, well, intuitively, the feasible set is a kind of the node is kind of a guarantee. It proclaims that I can solve the search problem, for these inputs, in some sense. So how this maps to the Kashmir-Wigderson game is I can define a monotone feasible rectangle for each of the nodes here by the following definition. So for a gate G, okay, take a node, the set is just all the inputs where G witnesses a positive, some kind of a positive difference between the two inputs. So the gate evaluates to true for the yes input and no for the no input. So let's look at the top node. The top node computes this monotone Boolean function. So it means that every yes input evaluates to true, every no input evaluates to false. So the corresponding feasible set is everything. So that's the first property I want to write down more abstractly, is that in a DAG I require, firstly, well, there's a unique root node, so maybe mention this. Such that the feasible rectangle is the set of all inputs. So you should see that this is somehow is going to be a generalization of just tree-like protocols. So if you look at the root node in a tree-like protocol, its associated set rectangle is basically the set of everything. It's like the set of inputs that pass through that node. A deterministic protocol would, in a single step, when, say, Alice communicates a bit, it would partition the rectangle into two parts. And this would happen recursively. This is a DAG-like model, so we have a different, this is basically the only difference from a tree-like protocol, the next property, which is that instead of having a feasible set and partitioning it into two, we just cover, the children of a node cover the feasible set of its parent. So if I have a node V with, so let's say it's a fan-into DAG, so every node has at most two children. I guess I should say non-leaf, so it has at least one children, but at most two. Say U and U prime. So then I require that the feasible set of the node V is covered by the union of the feasible sets of the children. So in a tree-like protocol, this would be equality of a disjoint union. But so far we have this generalized notion. So concretely for a monotone circuit, if I have fix an input, and if the input is part of the feasible set of a gate, so meaning the gate devalues to true and false for that input pair, in order for such a gate to witness such a monotone difference, it must be that one of its children also has this monotone difference. So how can a gate evaluate to true and false for a pair of inputs if neither of its children do that? So it's easy to check that this really happens. So that means that at least for monotone circuits, this property is satisfied. So the feasible set here is contained in the union of the feasible rectangles here. Okay. Sorry?
Why does this argument require monotone?
I guess if I had a negation gate, this wouldn't quite work. But you can do, again, this for general circuits, as long as you change the definition from not witnessing a monotone to just a difference. Okay, and so I have a final condition for the leaves of the DAG. So somehow the leaves of the DAG find solutions for the input. I have leaf, really. And the requirement is that the associated rectangle is monochromatic for the search problem. Okay, so let me define that. I mean, for Boolean functions, it was just what you would expect, and here this is a generalization for search problems. It just means that for each leaf, there's some associated solution which is valid or feasible for all this, for this whole set. So it means that exists some solution is valid for all x and y in the feasible set. So x, y, and that are in the relation. So we should again check what this means for a monotone circuit. So when I'm at a leaf, the feasible rectangle is just, for example, this is just a set of all strings that have a monotone difference in the first coordinate. Well, that kind of solves the Kachner-Victorson game. That's exactly, so the associated rectangle here, this exactly has found one of these coordinates where there's a difference. So the associated feasible solution is that where I is 1 for the first variable.
Do you assume the projection of S on x cos y is x cos y? Or otherwise you don't?
Yeah, okay. So yeah, we're kind of implicitly assuming that it's a total search problem. So for any input, there's some solution. That's kind of the interesting case here. And it's certainly true here. So every pair has one of these.
No, if both pairs are one input?
But they're very explicitly said to be.
Okay, so how come also the first condition I don't understand?
And part of feasibility is that it has a solution.
But x cos y contains also non-feasible pairs. Or maybe I'm missing something.
So I'm implicitly assuming that the search problem is total. For any pair of inputs, there's something that's a valid solution.
Which is not the case there.
Well, it's case for this particular problem.
Capital Y is f inverse of 0. Sorry, you just said capital X is f inverse of 1, and capital Y is f inverse of 0. And then, okay, capital X is
Oh, there shouldn't be any capital. Yeah, I was criticized about my handwriting before. Yeah. So yeah, this is really abstract. It's not clear why I need to take such a clean, self-evident model and define it in such a kind of weird manner. But this is somehow capturing a top-down interpretation of a circuit. And we should spend some time mulling over this. Like, what does it mean? Like, one immediate question is, how should I think about this? What kind of, in what sense am I solving the search problem? What's an operational meaning? And it's really subtle, actually. So I'll give you one, and we'll spend a lot of time on this later. So one operational meaning is that, so if I fix an input, let's see in what sense is this DAG solving the search problem in this sense. So let me highlight all the nodes for which this input is feasible. So the first condition said everything's feasible for the top node. The second condition says that if I have a feasible node, then at least one of its children is feasible for my input. So maybe this is also feasible, my input. And really, I can kind of traverse the circuit down, just applying the second rule, until I find a feasible leaf that is associated with a solution to my search for my input. So at least so far, now if I want to find a solution to my input, I can start at the root and kind of step down until I reach a leaf, which gives me a solution. However, this circuit provides something more, and it's really important. It's not like, so far what I've described sounds very much like a branching program, if you know what that is. It's a starting node, and you make decisions based on the input. Once you enter the sink, you output that. But this is a more, maybe a non-deterministic model too, is that there could be feasible nodes that aren't reachable by such walks. I mean, maybe I have a node here whose feasible rectangle contains my input. Well, I can still play the game. If I'm feasible at a node, I must be feasible for one of the children. So the DAG provides more guarantees. It says whenever I'm feasible for some node, not necessarily the root, but some, I can always find a solution by stepping down along feasible nodes. So there's also an interpretation of this in terms of something called PLS, in Turing machine complexity theory, polynomial local search. It's basically saying that you solve a search problem by defining maybe implicitly a DAG whose sinks gives you solutions to the search problem. But maybe I'm not going to spend too much time on that. So yeah, it's certainly a kind of a weird way of viewing a circuit. So the key theorem, which was proved by Rasborough, 95 or something, is that this characterizes monotone circuits. So if you take, I denote by rectangle DAG, the rectangle DAG complexity of a search problem. So the least size, least number of nodes in a rectangle DAG that solves the search problem, and in particular, if I specialize the search problem to a Kvartmer-Wigderson game. Then this is exactly the monotone circuit complexity of F. So I wanted to make this definition of a rectangle DAG by extracting it from a circuit. So it's clear that if I have, by definition, if I have a monotone circuit for F, I can construct a rectangle DAG. It's just one-to-one correspondence between the nodes. Rasborough says the converse holds, that I've listed enough conditions here that from these you can construct back a circuit. And it's basically an exercise. There's not a lot going on. And the nodes are in one-to-one correspondence with the gates of a circuit. Let me just say that for this second condition, if I'm looking at a feasible rectangle and I know that its children are covering it, there's two ways to cover a rectangle, like side by side or top to bottom. And depending on which of those happens in a rectangle DAG, that determines whether it's an AND or an OR gate. Yeah, okay, I should also mention, of course, that this is less known than something that's really famous, and that's to characterize just a circuit depth in a more familiar communication model. So that's actually where all this Kvartmer-Wigderson search problems came out. So you should compare such a characterization with just the deterministic communication complexity of the monotone Kvartmer-Wigderson game. Deterministic communication complexity in the usual tree-like model. It's monotone circuit depth. So, well, circuit depth is the same as log of formula size. So this is a method to prove tree-like or formula lower bounds. But for this talk, we really care about this characterization of DAG-like or circuit-like models. Okay, so that's some way to capture monotone circuit size. Now I want to capture the size of a resolution refutation in a language that is so similar. Let me first just remind what the resolution proof system is. So it's a system that is trying to refute unsatisfiable CNF formulas. So you pick some, that's a capital F, some unsatisfiable CNF formula. So it has some clauses. So that formula is an AND of these junctions of literals. And the resolution proof is trying to derive a contradiction from such an unsatisfiable formula by repeating this process where you take two clauses and derive a third using really any sound inference step. The important thing is that whenever you infer something, it needs to be a clause. So you can define it fancily as this, as I just did, as saying, use any sound inference rule. But there is, this often defined syntactically. The actual rule that you can use here, without loss of generality, is that if you've derived a clause that has a particular variable, okay, Z, I, and you've derived a different clause that has the negation of the variable, then you can derive the clause that's a union of these parts and these parts. So that's a sound inference rule in the sense that if for any truth assignment to the variables, if they satisfy this clause and this clause, then it needs to satisfy this clause. So, okay, I see puzzled faces, so let me maybe spell that out. So imagine some truth assignment to the variables here. There are really two cases. Does that truth assignment assign true to my variable here? If it sets this to true, then it sets this to false. It means that something in this clause is set to true. So hence this is satisfied because I included all these clauses. And the same case analysis holds. If this is set to false, and this is true, and something is in here is true under the assignment. So this is. So basically, you use this rule to derive new clauses until you can derive the contradiction. So you.
You mean an end of literals or
Yeah, ors of literals. I guess I should also mention, as a technicality, sometimes you also allow a rule that it's kind of silly, so called the weakening rule, where from a clause you derive the clause or some new variable. It's a technicality. But that's basically resolution. You can pick your favorite unsatisfiable CNF format, try to refute it or derive an inherent contradiction using these kinds of inferences. And what we care here is about the least size of a proof that does this. It's one of the most basic propositional proof systems that are studied. And we have plenty of lower bounds for this system. So I want to define this anew, but in exactly the same language I've been using.
But a proof is a sequence or
You can say it's like the straight line program definition would be, say, it's a sequence of clauses where each clause is derived. You can just write it as a kind of more topologically as a DAG.
Okay.
So
then just the edges correspond to direct inferences.
yeah, so each clause has fan in two, means that this is derived by the resolution rule from these two.
So class C4 in this case is just C1 bar?
Yes.
And the one on C3 is just Z2?
Yeah, okay, now, so I didn't want to fill them in because actually you can already derive a contradiction from here. But yes, so if you actually worked it out. So you don't really need such a large proof as I've put here. You can already infer, as you said.
That's not of Z1.
Not Z1.
The other one has Z2.
Okay, so
All right. Much smaller circuit, right?
yeah.
No, but
So okay, so you can put. Okay. No?
no, because Z2.
Well, I mean, okay, you could already from these derive the empty clause, which is the contradiction.
Oh, but
So-
can I object to that class C1 or is this okay? The fact that you have two arrows coming from these two into C1.
Yeah, so yeah, I shouldn't have gone in there. It was just a visual placeholder. So let's just assume that it was a valid example. Yeah. Okay, so let's give this top-down characterization for a proof. So far, it was kind of bottom-up. I said you started with these and you did logical inferences and you ended up here. But I want to flip it around as I did there.
What is your goal now? What do you want here?
I want a characterize this model top-down in a language that is very similar to what we saw for circuits. Because I want to make this connection between the two models. So the definition is really short. I call them query DAGs. So again, you can say solving a query complexity search problem. So now there's just one piece of input, n bits. So you need to find some solution. Okay. I also want to tell you, this is more abstract, but really what we really care about is specific types of query search problems. So that's kind of the query analog of what interested us for monotone circuits. And so these are, the interesting search problems are called CNF search problems. So these query DAGs will solve a CNF search problem. So let me denote it by S sub F. So this is, say it's an n-variate unsatisfiable CNF. Okay. And here as input, your n bits of input, it's just a truth assignment to the underlying variables of the formula. Okay, so this is, you should think of it as a truth assignment. Okay, and since this is an unsatisfiable formula, it means that whatever truth assignment I'm looking at, it can't satisfy all of the clauses. So any truth assignment, there's some clauses are falsified. The search problem is to find a falsified clause. So find a clause in this formula. So the formula is really AND of clauses. My notation for one of the Mika clause, such that the truth assignment falsifies the clause. So these are really interesting search problems because there's a kind of a tension going on here. Okay, I should say I also always implicitly, when I say CNF, I'm interested in CNFs of small width, even like 3 CNFs or something. So this condition you need to find, if the clauses are of width 3, then there are very efficient non-deterministic solutions where you just have to guess 3 bits in your input and check that one of the clauses is falsified. It's this typical NP type of a search problem where well, really total NP search problem. We know on any input there's some solution, and that solution has a small certificate. Testing this condition requires 3 queries to the input. So you could, I'm not going to make too big of a point about this, but you could even say that this search problem is, so there is this Turing machine complexity class TFNP for total NP search problems, and you could study similar problems in decision tree complexity, and this is a typical problem in that class. And actually there's kind of a converse. Any query complexity search problem that has low certificate complexity, you can actually write as a CNF search problem. But yeah, I'm not going to make too big a point about this. But I also want to maybe make the observation that these monotone Gaussian vectors in games have the similar property. The solution, if I just guessed non-deterministically an index, it's really easy to test that you found a correct solution. So the both are kind of TFNP problem, communication and query complexity. Okay, so now I want to define this query DAG, and it's the same definition I gave, but you just replace rectangles with subcubes. So the feasible sets are subcubes. So every node is associated with one. And again, the subcube meant you have, in your n-bit domain, you fix some number of bits, and the remaining are completely unrestricted. That's a set of such inputs. And the way it maps into this model is I can define this feasible subcube for every node here. So for a clause, in a resolution proof, the feasible subcube, you basically just negate a clause. So for each clause, the associated feasible set is the set of truth assignments that falsify that clause. Under this definition, everything just works. We can again check the three conditions that from a resolution refutation. Under this definition, you get a query DAG. So the first condition was to say that everything's feasible for the top node. Well, it's the constant zero function, inherent contradiction. So every truth assignment falsifies it. Everything's feasible. Okay, so we just changed a rectangle to a subcube. And the first says everything's feasible at the root. The second says if I have an input that's feasible for a node, it must be feasible for one of its children. And that follows simply from this sound inference rule. We're using a sound inference rule. So if I have a truth assignment that falsifies a clause, I claim it must falsify one of the children. Well, this was a logical consequence of these two guys. So for any truth assignment, if they satisfied both, they satisfy this. So just contrapositively, if this is falsified, one of these guys must be. So that means I'm at a feasible node. I can always move to a child. And the third condition is that I have monochromatic subcubes at the leaves. Well, I have a leaf which is associated with a clause of the original formula, and well, that exactly corresponds to a solution to the CNF set problem.
So what happens with this trivial derivation rule of adding an extra literal?
So I think I'm going to come back to it later. So it's basically, so one way to view it is that it allows us to well, really exploit the DAG likeness of a proof and keep the width of the clauses bounded. But I'll come back to that. Maybe it's not clear yet.
Isn't that type of edge a problem for this claim that if you falsify a node, you must falsify one of the children?
No. In fact, what I'm saying is not even specific to resolution. What I say works for any sound proof system. Like I only use the soundness of the rules. So when I do the weakening, it's still sound. So the argument needed nothing but soundness.
Okay, I see. But just confusing because when you write the deductions, they go downward.
Okay, yeah, sorry. Yep.
So if you do use that other inference rule, then you will have the same subcube for both of nodes?
Not quite. So, I mean, you're adding a new variable. So the subcube changes.
Well, but the set of inputs should always have it.
Sorry?
The input string will always have this variable.
So if my DAG contained a clause or a variable, and that was derived from just a single clause. So the feasible subcube, the negation of this, would be a smaller set as here. So this feasible set is duly covered. Okay, so let me just write down what I basically said or suggested, and I should kind of credit this point of view of viewing proofs top-down. I think it was first discussed by Butlank and also by Atserius and Dalmau. So, well, what you expect is if you look at the least size of a query DAG that solves the CNF search problem associated with an unsatisfied Bayesian formula, this is exactly the, well, resolution size of refuting F. So that basically completes this change of perspective. That I've now recast these two models in a way that they're defined using the same pattern, except they only differ in basically two places. So one is, instead of looking at rectangles, I'm looking at subcubes, communication versus query. And the other aspect is, what's the interesting type of problem that connects these to the two models? Well, they're monotone Kashmir games or CNF search problems. So we'll eventually want to use lower bounds for proofs to give lower bounds for circuits. So that means we do have to also invest some creativity in rephrasing problems of one kind to another interesting kind. So the whole proof strategy, I would say, consists of two steps. You want to equate the models and prove a lifting theorem, and then give reductions that we are looking at the right type of problem. Okay, so before the break, okay, let me actually state at least the lifting theorem, since we now have the definitions. So I should mention, what are the trivial relationships between the two models? Well, communication protocol can simulate a decision tree. So that, in this language, it would say that the rectangle DAG complexity of any search problem, two-party search problem, is at most the query DAG complexity. So let me be a bit careful here. So you could think of S as a query complexity search problem. There's n bits of input. You need to find a solution. But no matter how I partition the n input bits between the two players, okay, so maybe I just partitioned the input so that I can regard it as a two-player problem, can immediately simulate it with a rectangle DAG, because each subcube, so and of literals, can be simulated by a rectangle. So that's a trivial direction. I also mention an important parameter here is the width of a query DAG, or the width of a resolution proof. So if I have a resolution proof where the clauses are bounded, the number of literals is bounded by something, then it immediately gives a bound on the size as well. So if you have, let me just call it width of the least width of a query DAG that solves S, you get a bound on the number of possible nodes. There's no reason why in these DAG-like models you wanted to repeat a node. So if you have two nodes with a feasible set, you might as well identify those nodes. So these are kind of the trivial relationships. And okay, I should also mention, so historically, this kind of a connection is known as the monotone feasible interpolation technique, and it's already been used to show lower bounds in proof complexity from lower bounds in circuit complexity. So because of this kind of, the models are trivially related. But the whole point is here, we're going the other direction, the hard direction. So the kind of main technical statement. It's exactly what you would expect from last week. So for any query complexity search problem, we can characterize the rectangle DAG complexity of, it's the same construction as last week. You have a query object with n inputs. You can compose it with a gadget. We talked about the index gadget last time. Maybe I can remind you about that function. So it's this function where Alice holds a pointer into Bob's string of m bits. And I have a pointer and a string of n bits. They map to the xth bit of y. So for any query search problem, you can consider this lifted or composed version where the input variables to S are split between Alice and Bob according to this gadget. So we can characterize this complexity, and it's basically making all these measures the same. So this is n to the theta of the width. So implicitly, I also equated the sizes of these guys because it was sandwiched between. So if I wanted to prove monotone circuit lower bounds, the whole argument says I need to start something that's hard for this query DAG or resolution proof system, has large width. I get these rectangle DAG lower bounds, these kind of semi-artificial problems, like search problems composed with a gadget. So if I want something like that, I need, the second part of the argument is to reduce such search problems into monotone Karchmer-Victorson games. It's only then that we can apply this Rasparos connection. So I'm not going to go into the proof of this. I mean, we saw a non-deterministic lifting last week. And if you use those kinds of tools that relate large rectangles in the communication domain with small code-dimension subcubes, assuming such tools, the proof of this is like 2 pages. It's not too bad. So I'm going to say more about maybe the creative part in some sense of how do you view lifted search problems as monotone Karchmer-Victorson games later. But before the break, let me talk a little bit more about this width. So I want to give you yet another characterization. It puts a little bit more vibrancy in the definition, intuition, I would think. So I'll tell you a game theoretic characterization of the width complexity measure. I mean, we like games, they're kind of intuitive. See, it's really fun to work with them, whereas this was a bit static, a bit abstract.
Can you repeat what the first definition of the width of the search problem was?
Yes, so in this resolution picture, it was the number of literals in a clause. So I maximize overall clauses of how many width? Yeah.
Via the way you refute it, not directly.
Well, you can define it directly by saying it's the, in a query DAG, it's the maximum over nodes of the codimension of the subcube. But yeah, so here's another definition. Yeah, I'll find space somewhere. Okay. So game characterization of width. Okay, so this was, I think, due to Atzerius and Dalmau. And again, I fix a search problem, query search problem, n bits. And, well, I'm just reinterpreting a query DAG. So very little is happening, but again, conceptually, this is really nice. So when I was learning about this stuff, I think when you read the literature, the game is between two competing players, and the only kind of constant I found was change, in that every author used different names for the players. So I've also invented new names for the players. I call them Explorer and Adversary. So the Explorer really wants to solve this search problem, and the Adversary is trying to prevent that, or prolong Explorer. So the game proceeds in rounds, and the state of the game in each round, well, it's a subcube, of course, but let me use the equivalent language of a partial assignment. So the state is always a partial assignment. Okay. Now, of course, the set of n-bit strings consistent with a particular partial assignment is a subcube. Initially, it's the all-star assignment. Okay. Initially meaning at the top of the query DAG, the subcube of everything. And then it proceeds in rounds. In each round, the Explorer can do one of two things. So it can query a variable. It's kind of usual. So that just means that the Explorer chooses a coordinate and the adversary gets to decide what value is assigned to that variable. So adversary responds with a bit of his own choosing, and then the game state gets updated like this, that the ith bit just set to B. So that's a query step. I mean, so far we haven't really done anything. Like a decision tree would proceed like this. But then the new thing, what takes account of the fact that we're dealing with a DAG-like model, is that now you can also forget things you queried. So the Explorer can again choose a coordinate. And we forget the bit that was in that coordinate. So we just assign a star there. So the way this characterizes width is as follows. So just looking at the least W such that the I guess I should also define the end condition. I ran out of board. The end condition for the game, which is that you arrive at a partial assignment from which you can infer a solution to the search problem. So concretely for a CNF search problem, you arrive at a partial assignment that makes one of the clauses falsified. So, okay.
It's a subcube with the same solution. Am I right?
Yeah, it's just a redefinition of this. So maybe I don't even write it down. Like the associated subcube is monochromatic, so you know of a solution that's valid.
Of these partial assignments have the same solution.
Yeah. So good. So then the width is the least W such that the Explorer has a winning strategy in this game.
We don't care how long it takes.
That's right, that's right. So I don't know, the width of the state is at every step in the game is bounded.
So by that you need the number of
Yes. So yeah, we don't care about the length of the game, but again, there's no reason why a strategy would visit the same state many times. So again, the length is at most n to the width.
So can you just, so we've seen, I don't know, 5 different models maybe?
What, 2 different models? But many definitions, of equivalent definitions.
So can you just organize it before we go on a break and then forget everything?
So yeah, there really are 2 models only.
Yeah.
This model, with rectangles, and the other with subcubes.
Okay, sure. And then this game?
Yeah, so that would characterize one complexity measure of a query DAG, which is the maximum over nodes of the codimension of the subcubes. So for a single model, you can look at 2 interesting measures, which is the size, number of nodes, and the width. And it's one central theme in proof complexity that often the width kind of determines the size in some special cases. And in this case, we showed width is really a good proxy for size. So before the break, let me just kind of...
Just a quick question. Will you end up using the game formulation method?
Yes, right now. So before the break, I'll give you one example that you can sort of get your juices flowing or the break, just to kind of see how efficient the width might be. So here's the simplest search problem I can imagine. The first example. The input is an n-bit string, and let me hard code that the 0th bit, it's not part of the input, but I hard code that to be the 0, and the n plus 1th bit is 1. So you have n bits that are unspecified, and that's the input. So the search problem is to find the following pattern in the input, which is adjacent positions that are 0, 1. So if your string starts with 0, ends with 1, at some point you have to have this transition. The search problem is to find it. So if you're a decision tree, how would you find such a transition? This is too simple a question.
Read all the bits sequentially or something?
So yeah, that would be, as a decision tree, you would have read everything, which always works, but it's not efficient. So what if you needed to minimize the number of queries you're making? Right. So yeah, you would query the middle bit, and based on the outcome, you would recurse either on the left or on the right. So that's actually optimal. You can show that if you're a deterministic decision tree, the query complexity is log n. Okay, but what if you play this Explorer-adversary game, and you're an explorer? I claim there's now a better strategy in that you can do it with width less than log n.
So why is the width log n?
No, the width will be smaller, but the query complexity as a decision tree, if I didn't forget anything. So now I claim that there's power in forgetting because I can have smaller width. Sorry?
Basically 2 at a time. You forget the last one and read the next one or something like that?
Right, so in a binary search, you're doing this. So you have 2 boundaries that are closing in on it. And the point is that you can only remember the boundaries. There's constantly many bits. I think 3 if you work it out. You can forget everything outside the queries you made outside this interval. So this is the silliest example that shows that with the power of forgetting, there is some power to it. And after the break, I'm going to give you an even more dramatic example. There's a larger gap. But yeah, let's do 5 minutes.
This is a measure of memory.
Yeah.
In the game, you're allowed, so it goes in this order. So first you choose an index, then adversary respond, and then you get to forget one bit. Does it have to be
Yeah, I mean, okay, I should have said, so you do either query, either forget.
either?
Yeah. So you could do only queries or only forget operations.
If you forget, the adversary does nothing.
So whenever you query something, the adversary needs to respond.
0 or 1.
Yeah.
The adversary's not like, there's no like secret string behind the scenes that the adversary's committed to or anything, right?
That, yeah, it's interesting. So the definition says no, but for intuition purposes, it's useful to think of it like that. And okay, I should have really stressed this, that when you forget something and you query it again, the adversary is free to return a different value than it did before. So in that sense, the input keeps changing if you want. So the adversary, maybe it maintains the string, but it can change the string in those parts that are not part of Explorer's memory. So then let me give you a more dramatic example. I mean, this is already interesting actually for circuit complexity applications, as I'll maybe mention later. But an even more interesting example is a kind of a two-dimensional version of this. These are called Pepling games. How many B's are there? So this is a search problem where now the input comes in as a Boolean matrix. So the input looks like this. Actually, you can play this game on any graph, but let's look at a grid graph. So I can arrange the input bits as like this. And again, I hard code in some values. The left corner here is a 1, and then everything at the bottom is a 0. Everything at the right is a 0 as well. So for the remaining entries, those are given by the input. And the search problem is to find the following pattern in the input. A 1 followed by a 0, and also a 0 below the 1. So it's a pattern of 3 bits. And I claim it's a total search problem. This pattern must appear no matter how I fill this matrix in. I guess one, is that obvious? It's you can test whether the pattern appears at the very left upper corner. And if it doesn't appear, so maybe it didn't appear because this was a 1, well, then you find a 1 that's closer to these boundaries. So you can kind of play this game of following a path of 1s, kind of direct it right and downwards until you either hit a boundary, in which case you have to have the pattern. If you really got a 1 here, then your pattern would be found there. But this process eventually will find a pattern. And I actually already described a decision tree to find the pattern, which is you follow a path of 1s until you can't move any further. And it's kind of known that this decision tree is optimal. This type of a following of 1s, which in this case had cost root n, because you roughly need root n steps until you hit one of the boundaries. So as a tree-like model of computation, the query complexity is roughly root n. But again, now I claim that if you forget things, you can do much better.
But can you do a binary tree like that?
Okay, you could try to solve this using some kind of a binary search. So one is that you query everything here, and then you recurse on the left or on the right. Yeah, even if you just query that, you already done root n queries. So actually, to prove something like this, it's not so simple. Like, of course, a query algorithm could do all sorts of weird ways to try to isolate a solution. But yeah, how would you do this if you had the power to forget things you queried and you just want to minimize the width?
Just remember the current one.
Yes, just remember the current one. So again, maybe I think again, width 3 suffices. Okay, so that's already a huge gap. I should maybe mention like what's the best that are known for these kinds of problems. So this was defining it relative to a grid graph, but you could allow arbitrary constant degree graphs. And there are such based on expanders where you get query complexity even n over log n. So it's a huge gap between just tree-like computations and DAG-like computations.
Is it always sublinear whenever the degree is constant?
Good question. So so we know that for these sorts of problems that was optimal. So you can always do n over log n for this problem.
What do you mean these problems?
For pebbling problems, which I didn't define in full generality, but like you could imagine some other underlying graph.
Yes.
And then the nodes would be associated with variables, and it's a directed graph of fan out 2, and you would be looking for the pattern 1 followed by zeros. When I've promised that there's a root node has 1s and all the sinks have zeros. So that's how you define it more generally.
So for any constant degree graph, you can do it in n over log n, where n is number of vertices.
Yes. So examples like this that show gaps, they actually correspond to showing that this DAG-like resolution can be exponentially more powerful than tree-like resolution, where the underlying refutation is a tree. So I hope these examples illustrate this notion of width a little bit, that it can be powerful. But of course, when we want to prove lower bounds for DAG-like things, then we also need lower bounds on width. So as a third example, let me give you an example of a search problem that's really hard, even for width. Okay, and so these are called Titan formulas, Titan search problems. And let me define them in full generality. They're defined relative to a graph. You fix your favorite graph. And for a hard graph, you could choose this to be an expander. So it's a constant degree expander. It looks like this. And I also choose a special node, V star. And the input is an assignment to the edges of the graph. So the edges are associated with variables. So this input Z. And you can think of the input as specifying a subgraph of G. Just take the edges that are set to 1. So I have my host expander graph, and the input describes a subgraph of it. And so as a search problem, I promise that this special node I chose, I promise that this has odd degree in the subgraph. I mean, again, I could do that by maybe just hard coding the values of the edges. So it has degree 3. My dashed edge means it's not present, even though it's maybe an edge of the expander. So by this basic handshake principle, the number of odd degree nodes in any graph is even. So if I've exhibited one odd degree node, the graph needs to have another somewhere, and that's the search problem. So you need to find an odd degree node distinct from the special node. And so this is a search problem that comes, I said every search problem really comes from an unsatisfiable CNF search problem. And here, this is a particularly nice kind, because it comes from a system of GF2 linear equations that's unsatisfiable. So the degree of a node is just, so for any node V, you can write down a constraint that says it's not a solution. So that's just saying that the sum of the incident edges is even. So to kind of get this search problem out of a CNF or some unsatisfiable system of constraints, you would have a constraint for each node saying that its degree in the subgraph is even, except for the special nodes it would. So I claim that this search problem is really hard and it requires a width which is linear in n, especially when we play this game on an expander. Okay, so this is one of the most classical results in proof complexity. I think the earliest lower bounds for resolution proved lower bounds for these kinds of unsatisfiable formulas, where this search problem came from. And, well, I want to try to sketch this lower bound proof, actually. So why is it that you need large width? So our game says that to prove a lower bound, you have to give an adversary strategy that fools every explorer that remembers too few bits. And okay, let me say this again, which I didn't really say explicitly before, is that it's really important in this game that if the explorer ever forgets a bit and later queries it again, the adversary is free to respond with a different value than it did before. So an adversary strategy you could think of as like this, that the adversary keeps in his mind some full input to the search problem. And the explorer queries individual bits, but before every query, the adversary could change the input in any way he wants, as long as you don't change the bits that are in memory of the explorer. So let me sketch this adversary strategy against any explorer that uses sublinearly many queries. So the strategy uses this notion of, well, we call them critical truth assignments or critical inputs, which just means that they have a unique solution. So an example of a critical input is a subgraph which is just a path that ends at some node. So for any node, there's these type of input that has a unique solution exactly at that node. So the adversary starts like this. It picks one of these inputs where the unique solution is on some node V. The adversary always thinks of a critical input. The queries of the explorer we think of as, so the explorer might query things, and I kind of draw it like this. We always think of the queries as a cut in the graph. We're interested in, if this is a set of queries, think of deleting those edges from the expander and see how the expander splits into connected components. If the explorer has a budget of sublinearly many queries, so at any point I would have deleted a sublinear number of edges, then the expansion property says that you can't split the expander into, well, two linear-sized pieces. By definition of what it means to be expanding, if you have sublinearly many queries, you can only kind of cut away sublinear sized pieces, negligible fraction of nodes. So the key is this: the adversary always maintains a critical input where the unique solution is in the giant component. So the unique component that has most of the nodes in the graph. So when we start out, there are no queries. So of course, this is one connected component. And when these queries come in, our invariant is that the unique solution is kept in the giant component. So the only way that this could possibly fail is if the adversary is trying to isolate the unique solution in a small component. So it could start querying edges like this and trying to cut away a piece that contains a unique solution. But the trick that the adversary uses constantly is it moves the solution around by the following trick. So consider a critical input where the unique violation is there. What happens if I choose any path in the graph and flip all the variables on the path? So this is an endpoint. I flip the parity of this edge. That flipping the path would remove the solution here. Wouldn't affect the parity of the edges along the path, but at the end of the path it would again flip the parity. So it would effectively move the solution from one end to another. So if at any stage in this game I can freely kind of move the violation around inside a connected component. And so yes, the adversary strategy is just this. So when these queries come in, and I'm in a danger of now answering a query that would complete a cut, that would isolate the node inside the small, well, just before I answer the query, the adversary in his head flips a path and moves the violation somewhere else in the connected component, so that after the flip I can answer this edge according to the new input I keep in mind. And yes, I retain the invariant. The unique solution is in the giant. Okay, so yeah, it's really crucial that it's a kind of a dynamic game. That so yeah, I want to use this example to derive this main result of XOR SAT. This I claimed is the CNF search problem for a system of linear equations of bounded with even. So I could, so far in my strategy, I kind of sketched why if you started with this unsatisfiable formula, this Cyton, you can plug it in here, and this is a large lower bound. So far, we would get a lower bound for these composed search problems. So the next step in all of this is I want to reinterpret or embed this in a meaningful, for monotone circuits, type of a search problem. So it requires some creativity. So I'll tell you that reduction. It's a really generic one. You can do it for any type of, so if that was an unsatisfiable full system of linear equations, the Pebbling formula actually it comes from an unsatisfiable system of Horn clauses. So these are clauses that have at most, I guess, one positive literal. They're interesting because they're not NP complete, actually. Horn SAT is not NP complete. And this binary search example, that's like two SAT or two CNF. The clauses were of just with 2. So all of these types of different families of CNF formulas, they fit into this framework. So let me be slightly general, and instead of this XOR sat, I can just define a CSAT function for any set of constraints. So this is a finite set of k-array constraints. So maybe just to spell out, my first example came from a formula that has the following constraints. It used a singleton variable, I guess for the first bit. I required it to be 0. The last I required to be 1. And this pattern you needed to find that corresponded to falsifying a clause that said Zi implies Zi minus 1. So the corresponding set of constraints for such as would just involve both singleton clauses and implications of 2 variables. So that would be altogether 3 different constraints. And for these examples, it would be just, well, depending on the degree of the expander, it would be all GF2 linear equations involving this constantly many number of variables. But yes, you can define this for any set of constraints. And yeah, I guess I never defined exactly how this XOR sat function was defined, but this is now the definition abstractly. The input to the function is just, well, a set of constraint applied to n variables. So if there are k-array constraints, there are at most n to the k different k tuples of variables, and then you can choose which constraint to apply to them. So the input bits are literally in correspondence with all possible constraints applied to n variables. The input is interpreted as a subset of constraints, and we output 0 or 1 based on whether or not it's satisfiable. So the input x interpreted as an indicator vector for a set of constraints, and I output yes if that set system is unsatisfiable. So I guess I should say it would maybe be more natural to say that the yes input were satisfiable, but I need this to be a monotone function. I need it to be the case that if I flip 0 bits into 1 bits, meaning I include a new constraint, the function should only be more likely to output 1. In this case, the system is only more likely to be unsatisfiable. So that's why we define it this way. So I claim that if you start with any formula with constraints from this set, this is the key reduction, so if f, capital F, is it's a CCSP, so that just means it's an AND over constraints from this set, and it's unsatisfiable, which you can always rewrite as a CNF formula, by the way. Everything is bounded with. Then, well, we're interested in the CNF search problem, for which we have with lower bounds. And if I look at the communication version of it, composed with the gadget, well, then I can embed this inside the Karchmer-Victorson game for CSAT. So if this had maybe n variables, then this will have some poly in n variables. Maybe we lose some polynomial factors there. So this is interesting because there's this feeling that these problems are kind of artificial. Like we had this search problem, and we plugged in gadgets. It seems like it's just, it's some weird obfuscated problem. So this is really nice that these a priori weird-looking search problems actually embed in a really natural game. And you get meaningful lower bounds for the CSAT problems. Okay, so let me kind of draw a picture of the reduction. It's really sleek. I should have realized this reduction years ago. It's really abstract too because it works for any set. Prior work has basically done similar things for specific choices, but this is the most general lemma you could hope here. So let's do the reduction. So let me kind of draw a picture of what this search problem looks like. So I have my F, which is this fixed, unsatisfiable system of constraints. So it has some number of variables. So V1, V2, let's say 4 variables. And then some constraints between them. And for simplicity, visual simplicity, let me just use binary constraints. So some of the variables are in constraints. The edges represent the constraints. So that's now fixed. And in this search problem, for each variable is the output of an indexing gadget. So as input, Alice gets this pointer for each of the 4 variables. And Bob gets this m-bit string for each of the variables. So y. So I want to draw a picture of this actually. So this might be one of the n-bit strings. So it's something, 0, 1, so on. And I have one of these strings for each of the variables. Okay. And Alice has pointers into these strings, which I draw as I replicate again these tables. So Alice has pointers. So I draw that as simply a highlighted cell in each table. Okay, so the meaning of the gadget is that this variable receives the value that is Bob's bit in this position. So I guess it would be 0. So this variable receives that value. So for all the variables. And again, you need to find this falsified constraint under this truth assignment coming from the gadgets. So the reduction is really simple. This is the inputs the players have for this game. And now I need to say, how do they interpret their inputs as inputs to the Monotone Carchmer-Victorson game? And they just do this locally. They don't communicate anything. They just kind of transform their inputs. Well, so Alice's transformation is really simple. Alice takes the fixed unsatisfiable formula and embeds that amongst the new variables. So I interpret each entry in this table as a new variable. I started with 4, but now I have 4m new variables. So these are the underlying variables of this this function. This is really 4m. So Alice takes this, embeds it here. So just renaming variables. So this would be the first variable. Next. Next. Okay, isomorphic copy. So concretely, the input Alice would produce for the Carchmer-Victorson game is this set of constraints. So under this interpretation, I really get a one input. Because this was unsatisfiable, I just embed it here. It's still an unsatisfiable instance. Okay, so that's at least a valid input to the monotone Cartman-Victorson search problem. And now Bob needs to create a satisfiable instance of this CSAT, a zero input. And the way we do it is we just look at, for binary constraints, we just look at each possible pair of entries, and we include the corresponding constraint in Bob's input. So let's say, well, we interpret Bob's input here as an assignment to the new variables. So for each binary constraint, I add it to Bob's system of constraints. I add all such things as long as the constraint is satisfied by Bob's assignment. So this assignment y. Okay, I look at each pair, and I add these constraints that are satisfied. So it's a large set of constraints. And I claim it's a satisfiable instance, of course, because y here is a particular truth assignment that satisfies all of the constraints. So yes, indeed, we do get that Bob produces I guess this is right. So far I've taken the inputs here, produced inputs here, but for a really proper reduction, I also need to tell you how every solution to the monotone Cartman-Victorson game gives rise to a solution for the composed search problem. So what is a solution here? Well, it's this bit where Alice has a 1, Bob has a 0. But in this case, the bits corresponded to constraints, so it means it's a constraint that Alice has, but Bob doesn't have. So maybe, in this example, maybe this is a constraint that Alice has, but Bob doesn't. So Bob did not include the corresponding constraint in his input. But I claim that in this case, we have found a solution to the composed search problem. Namely, it's this constraint. Now that's the constraint that gave rise to Alice's particular one here. And yeah, it's simple to check. So I claim this is a solution. So the gadget outputs give values to this variable and this variable that don't satisfy this constraint. Well, why is that? Well, it's basically because the output, these variables receive values exactly the endpoints here. And Bob didn't include this constraint in his input, or in his instance. So that means exactly that the endpoints, whatever they were, they're not a satisfying assignment of this constraint. Yeah, so that completes the reduction. Yeah, I guess we've traded here generality. You can do it for any set of constraints with, I don't know, followability. But so, I mean, you could run the same kind of an argument for really concrete unsatisfiable instances. For example, if you did it for this, like the picture here would be topologically just a path, I guess a directed path, where each of the edges here was an implication. So if you ran this, you would reduce the composed search problem, this binary search problem, inside like 2SAT, which is basically SD connectivity. So if you look at the CSAT problem for clauses of this type, we're just asking, we're given some variables that need to be assigned true, some false. That's like defining S and T, at least set of S's, set of T's. And I'm just asking, is this satisfiable? So it's exactly unsatisfiable if there's a directed path of implications from the true variables to the false variables. So in fact, in this framework, you can also get lower bounds for not so for Explorer-adversary, for SD connectivity, and for other problems. So I should mention, you can't prove any monotone circuit lower bounds for SD connectivity because there are polynomial sized ones. However, you can prove monotone circuit depth lower bounds. So the I mentioned the query complexity here was log n, and there's a lifting theorem not for DAG-like size, but for tree-like size, which is like formula size. And that's how Kashmir-Victorsen showed like log squared lower bounds on the monotone circuit depth of SD connectivity. So yeah, general framework. So this basically completes the cycle.
So where are we losing the fact that this seems to give like an n to the omega of n?
Good. We lose in having had to blow up the number of variables from n to 4m, where m needs, for current proofs, needs to be chosen to be some kind of, 4 is n. But this needs to be chosen as a large polynomial in n. But if it was, so n variables, n times m, if m was a constant, you wouldn't lose anything. And that's why this proof would give you these truly exponential lower bounds if only you had lifting theorems for constant size indexing gadgets. Okay, so I have maybe 15 minutes left, and I want to try to give a glimpse into what comes next. Like, this works perfectly well. Monotone circuit lower bounds were known since the 80s, and now we just have really fancy general machinery to churn out such lower bounds. But I want to go further. So what are the next kinds of DAG-like models we need lower bounds for? So this is a bunch of open problems. This kind of recent perspective. So maybe the questions I want to work on here at IAS. So most of the motivations come from proof complexity. That somehow resolution was a very basic system, but there are increasingly more powerful systems, and you could instead of looking at the proof systems, you could look at these communication DAG-like models and prove lower bounds there to yield lower bounds for proof complexity. So here are some increasingly powerful DAG-like models. I guess I should mention some models that are not more powerful, but they seemingly might seem to be. So we had rectangle DAGs whose feasible sets were rectangles. And what if I allowed DAGs whose feasible sets were computed by efficient tree-like communication protocols? So want to draw pictures. So we know how to prove lower bounds for these DAG-like models where the feasible sets are rectangles. Here's a picture of a rectangle. Okay, we can do this. But what if instead I allowed the sets to be sets computed by efficient deterministic protocols? Well, any deterministic protocol efficient gives it's a Boolean matrix with an efficient partition of its entries into monochromatic rectangles. Okay. Well, the punchline is that these are no more powerful than simply rectangle DAGs. If you have feasible sets that themselves are disjoint unions of rectangles, well, you can convert them into just rectangle DAGs. Basically, you can take the communication protocols and bake them inside a rectangle DAG. Maybe another way to say this in the language of circuit complexity is that if you have a circuit whose internal nodes compute not just AND or OR, but arbitrary monotone functions of low monotone circuit complexity, that doesn't really change the model. You can replace those gates with the actual implementations of them. So I'm not saying much here. So this doesn't really add any power. Like, we can prove lower bounds for DAGs whose feasible sets are these. So you could ask, okay, what's the simplest kind of a shape for a feasible set that goes beyond deterministic protocols? And one such example is, I call them triangles. So that's a set like this. So it's a set, Boolean matrix, such that there's some permutation of rows and columns, so that each row and each column is monotonically decreasing or non-increasing. It's also, in communication complexity, we sometimes talk about the greater than function. Like, if you have two binary strings interpreted as numbers and you ask which one is larger, basically this is the communication matrix for it. So these you can consider. The motivation to do this comes also from proof complexity. So these roughly are the communication analogs of proof systems called cutting planes. So this is it's a strengthening of resolution. Instead of having disjunctions of literals as your nodes or lines, you instead have linear inequalities. So a line in the proof, instead of a clause, it's an expression like this. Have some real coefficients. So yeah, it's just a linear inequality in the space of your n bits. Now, it simulates resolution because you can express disjunctions of literals as linear inequalities, or at least interpreting these as Boolean functions, outputting 1 whenever this condition is true for a Boolean assignment. So these truly are more powerful than resolution. For example, you can refute pigeonhole principles using these kinds of proofs. You can't do that with resolution. And these lines, they can be simulated. This is again the trivial direction using triangle DAGs, which again correspond to this communication notion of, I have a number, you have a number, which one is larger? That's essentially a communication protocol for evaluating such a condition. Now, we can prove lower bounds for these. Again, even I think since the late 80s or early 90s, this kind of an extension was done. For triangle DAGs, you can prove lower bounds, and in fact, our result holds even there. You have to work a bit harder, but not much. So a one-line reason why triangles are not that much more complicated than rectangles is, okay, look at the picture. You can find inside each of these a large rectangle. if you have a large triangle, you can find this upper rectangle. That's the first observation, but you work a little bit harder and you still can prove lower bounds. So let me then mention for what models for which we can't prove lower bounds yet.
The lower bounds for this will be weaker than the lower bounds for rectangle or not?
I think the current state of the art is we have the same lower bounds. The best ones, by the way, not using this method, but quantitatively, since you care about it, is something like cube root of n here. Okay, this is not our result, but for another function for both rectangle and triangle DAGs. So here's the easiest thing. We don't know how to prove any explicit lower bounds. Call them equality DAGs. And they're motivated by a proof system called, again, a strengthening of resolution. Resolution over linear equations mod 2. So these are proof systems where each line is testing it's a disjunction of linear equations. So okay, you can write them like this. You have some vectors. So this is all GF2 arithmetic. So you have a condition like this and more of them. Altogether, say K. And again, so it's important here that the kind of power of this model comes from having. So let's put it this way: if you look at proofs that have small width in this sense, so each line is a disjunction of only few linear equations, then those are lines that you can evaluate efficiently using a communication protocol. Again, like no matter how the input bits are partitioned between the players, to test a condition like this involves communicating a single bit. Like I tell my parity of my variables involved in this, you tell your parity, and you check. So if you have only, polylogarithmically many such tests, you can decide this condition with a deterministic protocol. However, if I allow lines that have maybe close to, many, at a maximum, I guess you have n linearly independent equations, then you can't simulate them anymore by deterministic protocols. So you get a model that's more powerful than what we know to prove lower bounds. And the appropriate kind of communication picture here, what I call an equality DAG, is a set of feasible sets like this. So they are kind of block diagonal matrices. So you have a bunch of rectangles, and they lie, okay. Okay, but the point to repeat is that these are only more than what we can do deterministically if there are many of them. Like think of the identity matrix. No way to partition it into monochromatic rectangles efficiently. It's one per diagonal element. So that's amongst the simplest things where we don't know how to prove lower bounds. And somehow I'm just not scared of these. Like you can prove lower bounds for randomized communication protocols, and these you can compute with randomized communication protocols. So it's weird that if we include sets that are easy for randomized protocols, for DAGs, then we don't know how to prove lower bounds. there was also, this is something I recently learned, let me just quickly mention, yet another model, but it's not really a new model, which is, let's call them K-triangle DAGs. It's motivated by resolution over cutting planes. So the definition is the lines are disjunctions of linear inequalities. I'm going to write that down. But the picture is, for the associated communication DAG, is that there are sets that are intersections of K triangles. So here's one picture. So I had maybe one rectangle here, one rectangle below, and I intersected them. I got a shape like this. So that's been long open. I think this proof system was introduced by Putluck in late 90s. And somehow equalities are special cases of intersections of two triangles. I mean, I guess you can see it. You could have like one triangle that fills everything above, another triangle filling everything below, and this is the intersection of the two. Okay, and all that I have time to mention is that in fact, beyond appearances, DAGs with these types of sets are equally powerful. I mean, this was trivially a special case, but there was just a couple of months ago, a master student, I don't know if I can pronounce the guy's name, Folvarchny, who observed this, that equality DAGs can efficiently simulate K-triangle DAGs. So this means that it's a really neat situation. There really is one new model for which we lack lower bounds. It's basically these sets, we know how to compute them with randomized protocols, and we know how to prove lower bounds for randomized protocols, but when they are in the DAG-like setting, I don't know, we don't currently know how to do that. So, okay. So I think I should end there. Okay, thank you.